Hello friends. So today we are going to discuss three questions, and these three questions are from electrostatics. Okay, and just 1 second. Okay. So we are going to discuss three questions, and these three questions are from electrostatics. Okay. And in the first question, it states that three positive charges A, B and C of 3 into 10 to the power minus 6, 2 microcoulomb and 2 microcoulombs respectively are located at corners of an equilateral triangle of side 0.2 meters. And based on this we have two questions. Part A, find the magnitude in newtons of the force on each charge. Part B, find the magnitude in newtons per coulomb of the electric field at the center of the triangle. So this is quite basic question, only the way the question is framed is a little bit different, because usually in the textbooks you must have seen the question that find the magnitude of the force. Here it is written find the magnitude in newtons. Okay, so units are included, and this is only just to, you can say, create a little bit of increase the length of the question. Rest of things are quite simple. So let us draw the basic figure, and we are given equilateral triangle, and let us consider these triangles coordinate A, B and C, and the charge at A, let us suppose, is our QA, B is our QB and C is our QC, and QA is our 3 microcoulomb, QB and QC are same, so QB is our 2 microcoulomb and QC is also our 2 microcoulomb. And in the first part we are supposed to find out the force, and so let us assume that we have a equilateral triangle, and side of equilateral triangle is given to us, that is 0.2 meters. Okay, so you can see that side of the triangle, let us suppose that is given as A, and A is our 0.2 meters, and the charges is our QA, which is our 3 microcoulomb, and then we have our QB, which is our QC, is equal to our 2 microcoulomb each. Okay. And we are supposed to find out the force on each charge, and all the charges are same. Let us assume they are positive, so there will be only the force of repulsion. So in the first part we are going to find out force on each charge. And so obviously this is our A distance, and this is also our A distance, and this is also our A. Therefore we can say that the force on charge A because of B will be equal to force on charge A because of C. Okay, that will be same, and therefore we can write K, and we have this as 3 microcoulomb and 2 microcoulombs divided by our radius distance square, and this will be coming equal to as 1.35 newtons. Then is our FBC, and that will be equal to our K, and this is both are same, so this comes as 2 into 10 to the minus 6 divided by 0.2 whole square, and this will be coming equal to as 0.90 Newton. Okay, so this is our this force, and now we can also find out the force on, let us suppose we want to find out the force on charge A. Okay, and so force on charge A, so this is our charge A, and somewhere here is our B, and this is our C, and the B is going to apply a force, let us call this as our FB, and similarly there will be a force because of charge C at A, and the angle between these two forces will be equal to our 60 degrees. Okay. And so we can easily find out the resultant, because FB and FB will be our same. So force on charge A, let us suppose we call this as our FA, then we can say that our FA will be equal to, and let us assume that our FB is equal to our FC, and that is equal to our F. So we can say that is equal to our F square plus F square plus 2F square and cos of the angle between the two. So the resultant will be somewhere here. Okay. And so we can, from here we get that value of F will be approximately equal to 2.34 newtons. And similarly we can find out force on charge B, and that will be same as force on charge C, because so you can say that force on charge B and C, because they will be same, and therefore we can write same that our FB will be equal to, we have 1.35 whole square plus 0.90 whole square plus twice 1.35 0.90 and cos of 60 and its square root. And we get from here that value of the force on charge B, that is FB, will be equal to 1.96, and that will be also equal to our FC. So we got the forces on there respectively for the charges. Okay. And next we come to the part B, and where we are going to find out the electric field at the center of the triangle. we have part B, and so this is our A, B and C, and let us suppose this is the center of triangle, which is denoted as naught. Okay. Therefore we can say that the distance of each vertex or each charge from the center of triangle, let us suppose, is of R. Then this value of R will be equal to side divided by square root of 3, and this comes as 0.115 meters. And we know the standard formula that field due to each charge, field due to a charge, then this field is our E, and that will be kq upon r square. So using this formula we can easily find out our electric field because of A, and that will be equal to 9 into 10 to the power 9, and Q is our 3 into 10 to the power minus 6, and R is our 0.115 whole square. So this comes as our 2.05 into 10 to the power 6 Newton per Coulomb. And then we can find out electric field due to B, and that will be same as electric field due to our C. So this comes as 9 into 10 to the power 9, and charge is our 2 into 10 to the power minus 6. This is 0.115 whole square, and this comes as 1.35 into 10 to the power 6 Newton per Coulomb. But we have to remember that this is our center O, and this is charge A, and this is a positive charge. So because of this, the electric field, this is our center O, and because of this this charge at A, the electric field will be in the away from that. And similarly, this is our charge B, and then this charge B is going to give us electric field in this direction. And then we have our charge C, and it is going to give us electric field in this direction, that is our EC. And the angle between this EB and EC will be equal to 120 degree. Okay. And therefore we can find out the resultant of the electric field because of this EC and EB, and that resultant will be somewhere in this direction, and let us call this resultant as our E. Therefore we can say that resultant E will be equal to, we have our EB square EC square plus twice EB EC cos of 120 and its square root. But the magnitude of EB and EC is same, so we can just replace it by one of the variable. So we are going to get this as our E will be equal to, this will be our twice EB square, and this be also our twice EB square, and 120 cos is minus 1 by 2, so this will be coming as our EB, which is equal to 1.35 into 10 to the power 6. Okay. And therefore now we can find out our net electric field at point O. We can say net field at O, which is our center of the triangle, and let us call this as our E net. So this E net will be equal to electric field because of A minus the resultant electric field, that is our E. And EA is our 2.0225 into 10 to the power 6 minus, and this is our 1.35 into 10 to the power minus 6. Okay. So we get our the net electric field at point O will be equal to, this will be our 6.75 into 10 to the power 5 Newton per Coulomb. Okay, so this was comparatively easy. Only thing we have to take care that at point O it will be consisting of the net electric field and the resultant of EC and EB. Okay, that's the only thing we have to take care of it. Okay. And okay, so let's start the next question. The second question, it states that a semicircular wire of radius r lies in a plane and carries a uniform negative linear charge density minus lambda. Show that at any point on the axis, the line through the center perpendicular plane of the semicircle, the electric field vectors all point towards a single fixed point in the plane of the semicircle. Find the location of the point. Okay. Here the question is, you can say they have twisted a little bit language, but if you look to the figure closely, it is quite simple. We have a semicircle wire, and this is the center of this semicircle, and this is the axis, and that is perpendicular to this, we can say to the plane in which the wire is there. And it says that there is a single fixed point which is denoted somewhere here, and the entire electric field will be direction wise pointed about this. Okay, irrespective of the point wherever you take. Okay, suppose here we have taken, in the question the figure is given, so here we have 3 points, and we can clearly see that all these 3 points are pointing toward the same point. Okay, and finally we have to find out what will be the position of this point. Okay. And let us call this point as our O. Okay. And R is the radius of this semicircle, and we have to remember this is a negative charge density. Okay. So in this case we are going to let me draw it in a more traditional way which we are used to. So we consider, let us suppose this is our x-axis, and on this we have a semicircle wire, and suppose this is the center, let us call this center as C, and this is our origin. Okay. So on the left side we are going to get minus R0, on the plus side we are going to get plus R0, and the axis on this C, so this axis we have to remember will be perpendicular to this point C. Okay. And let us call this as our Z axis. Okay. And on this Z axis, and please remember this Z axis is perpendicular, okay, at center C. And so on the Z axis let us consider a point P, okay, and whose coordinates will be given as 0, 0, Z. And on the semicircle let us consider a small element, and that element is our d theta at angle of theta. Okay. And this small element is, suppose our having a charge of dq, and r is the radius. Okay, now we can define the coordinate of this small element. So we can say a charge element on the semicircle and this coordinate we can write as our r cos of theta and our r sine of theta and 0. And in this case we have to remember that our theta is going to lie between our 0 and pi. And for this charge element we can write its value of charge, that is dq. So we can say that our dq will be equal to minus lambda r and d theta. And so let us join this point and let us call this distance our r. Okay. So once again I am saying this z is nothing but perpendicular to this plane. Plane means the in which our this wire is lying. Okay, so from here we can clearly see that axis is perpendicular to the plane in which the wire is lying. Okay. Therefore we can say that distance to P, distance to point P, that is of r, will be equal to our r square plus z square and its square root. Okay. This is more clear from this. Okay, let us suppose this is our point P, so obviously this will be our z. Okay, and we have taken the charge density somewhere here. Okay, so this entire distance will be our r, and if we join this one, so this is our small r. Okay, so from here it is more clear, and we can find out the vector from the charge element to P. Okay. So we can say the vector from charge element to point P, and let us call this as our r vector. This r vector will be equal to minus r cos of theta minus r sine of theta, and this is our z. And based on this, or we can say we know the standard formula of our electric field because of this charge element dq. We can write that our electric field will be equal to k, and this comes as a dq, our r cube, and this is our r vector. And we can substitute value of dq and everything, so we get this as our k. dq was our minus lambda r d theta, and r cube will be our z square, and this is our 3 by 2, and our vector is our r cos of theta minus r sine of theta and z. And we can further modify it or rewrite it. We can say this is equal to our k lambda r d theta r square plus z square 3 by 2, and this gives us r cos of theta r sine of theta and minus of z. And now Okay, so in this case, because of the symmetry, you can easily see that one of the component is going to cancel out, only two components will be left. Okay, so let us find out which component will be left and which component will be balanced out. And for that, we can just make a little analysis of that. So we can say that our electric field was our dq, and we are going to take its modulus because of this, and this is our r vector and our r cube, and this we can divide into our three components. Okay. First will be our x component, so this will be x giving us minus k, and this is our dq r vector r cube, and this comes as our r cos of theta. And we can write its y component, and this is equal to minus k dq upon r cube, and we have our r sine of theta, and finally we can write it as z component. This is our k dq z upon r cube. Okay. Now we can clearly see that only there are two components, x component and y component, which are dependent upon our theta. Okay. And if you look closely, theta we have taken as like this. Okay. So this is our angle theta. So similarly, a symmetric point to this on the opposite side is going to give us angle of minus of theta. Okay. And we know that cos of minus theta is cos of theta, whereas sine of minus theta is minus sine of theta. Okay. So it means this y component is going to balance out each other. Okay. We can just make a short discussion about that. So we can say that our this E of y for our positive angle theta is proportional to our sine of theta, and the same angle for our minus of theta will be proportional to minus sine of theta, and if we add them, we get that their summation, that is our dE y for positive plus dEy for our negative will be equal to 0. Okay. From the figure also it is quite clear, but we have to remember that with respect to point P, they also have to be symmetric. So this is point P, and from the left side this should be our distance r, and on the right side also we are going to have this distance r. So this point P, we have taken this point as, okay, let us take this point, got lost. Yeah, so we have taken this point as P, and let us take point this as our A. Therefore, so this is, if this is A, then this should be our A prime. Okay. So this A and A prime are symmetric for all the respects with respect to distance r and respect to angle theta. Only difference is that with respect to it's a positive as well as the minus angle. So it means the y component is going to be balance out each other. Okay. Now we can easily find out our electric field in x direction. So we can say that our total electric field in x direction, this will be equal to over k lambda r square divided by r square plus z square 3 by 2, and this goes from minus pi by 2 to plus pi by 2, and we get this as cos of theta and d theta, and this integral is going to give us an answer of 2 only in the integral part. Okay. Therefore, we can write the electric field in x direction will be equal to 2k lambda r square divided by r square plus z square and 3 by 2. Okay. Similarly, we can solve it for our z also. So we can say electric field in z direction will be equal to k lambda r z r square plus z square 3 by 2, and this comes as d theta minus pi by 2 to plus pi by 2. Okay. And so this gives us k lambda rz, and this will be multiplied by our pi, and denominator will be our r square plus z square and 3 by 2. Okay, so we are only having two components. We are having x component and we are having the z component. Okay, so our y component is balanced out. Okay, so we have to remember this thing. Okay. And now in this particular case, if you look closely, you can clearly see that any point O, this angle is changing. Okay, as the point P is changing, first it is here, then we can take this and this. Okay, for any point P, we are going to get a different angle of the electric field at point P. So we are interested in finding out this particular angle, and let us call this angle as our alpha. Okay, and we can also say this is nothing but the direction of the electric field. Okay. So you can say that our direction of the field, and we know we can represent it as our tangent of alpha, that will be equal to our z and our x. Okay. And so we can say our tangent of alpha, and our z is our k lambda rz pi. So this is k lambda r z pi divided by r square plus x square 3 by 2 and whole divided by 2k lambda r square, 2k lambda r square, and denominator is same, 3 by 2, and this we can denominator goes away, k, and we have this lambda, and r goes by this r. So we are left with only our pi z and divided by 2r. Okay. So from here we can clearly see that for any value of z, we are going to get only one value of alpha. Okay. Therefore we can say that same line for every value of z. Every value of z. Okay. Or we can further write it as that all field vectors, point toward a single fixed point. A single fixed point. So this was our part A, and then we have to find out its position. Okay, and for that let us assume that this fixed point is the fixed point is at x0 from the center. Okay. Therefore, we can write once again, we can write our tangent of alpha will be equal to z upon x0, and we just found out our tangent of alpha, so we can just equate them. This becomes as over 2r. So this z and z cancel out, and this gives us that the value of this x0 will be equal to 2r upon pi. So this is our location of our this x0. And we come to the next question. And in this question, it states that two long thin parallel rods are a distance 2b apart, are joined at one end by a semicircular filament of radius b. A uniform linear charge density lambda is distributed along the entire filament. Point C is the center of the semicircle. So based on this, we have two questions. Show that the electric field at point C is 0, and part B, consider the analogous two-dimensional setup involving a cylinder and a hemispherical end cap with uniform surface charge density rho sigma. Using the result from part A, do you think that the field at the analogous point C is directly upward, downward, or is 0? Okay. So in this case, this question looks a little bit tricky, but the solution is quite simple. Okay. Solution is not a big. So in this case, we are given that we are having a semicircle. Okay, so this is a semicircle, and the center of this semicircle is given as C, and to the left and right it is connected by a rod, and the distance between the rods is given as 2b, and the radius of the semicircle is given as b. Okay. And we have to find out, or we can say we have to prove, in this case the electric field at the center C is equal to 0. Okay. So this is the basic question. Okay. And therefore we can so solution is quite easy. And so if we assume that center is C, and then center C is our, let us suppose this is our origin, so we denote this as O comma O, then our left will be our minus of B comma 0, and the right will be our plus B comma 0. And the charge density is given to us as a lambda. And for that, let us consider, so first we are going to consider this our semicircle, and for semicircle we are going to consider a small element, and that element is at angle of theta, and the small element is, let us suppose, is having a charge dq. Okay. Therefore we can say for small element dq, we can write that the electric field will be equal to K and dq upon this is our r cube and our r unit vector. And then actual to this, according to the question, we can formulate this equation again, but for the time being we are going to consider this part only. Okay. And therefore we can say that for the semicircular arc, because electric field at C will be the contribution of two parts. Okay, one will be because of the semicircular arc and other will be because of these two parallel lines. And so we can say semicircular arc contribution. Arc contribution. And we have already said that we have considered a charge element, and let us suppose this charge element is our ds, small element ds. So you can say for small element ds, which is at an angle of theta, so we can say this ds will be equal to our b times d theta. Okay, and d theta is this small angle, so d theta. And therefore we can furthermore write that the charge of the small element dq will be equal to lambda times b, and this comes as our d theta. And we can also write this position of this element position of the element will be equal to over b cos of theta and b sin of theta. And furthermore, like in previous question, we can write the vector to C. Vector to C, and that is our r vector will be minus b cos of theta minus b sin of theta. And for this particular case, we know that our r is nothing but our b. Okay. Therefore, we can write that the field from the arc element, the field from the arc element is nothing but our ds. Okay. So let us call this as our dE arc, and this dE arc will be equal to k, and total charge is our dq, which we already know is our lambda b d theta, and this comes as our b cube and b cos of theta and minus b sin of theta. Okay. And okay, now we come to the contribution because of the rod. Okay. We can say straight rod contribution. Straight rod contribution. And for that, let me redraw the figure here again. So this is our semicircular arc, and we are going to consider only one rod, and we have already assumed that this is the element which we had taken, and this element was at angle theta. So we are going to extend this element to the opposite side of the rod to this point. So So this angle will be also equal to our theta, and let us suppose this is our L. So obviously this will be our B. This is our radius circle B. Okay. Therefore, so we can say that we can write the position of the rod element. Okay. Here also, like we have taken this as our ds, similarly here also we are going to take a small element that is equivalent of ds. Okay. Therefore we can say that position of the rod element on the rod. Therefore we can say that position of rod element, let us call this a ds prime, is our ds prime, and we can write this will equal to b comma l. Okay. And now we can find out vector to c. C is our center. So we can say that our vector to c, and that will be our r vector, and that will be minus b minus of l, and we can easily find out its magnitude. Magnitude is our r, and that will equal to b square plus l square. Okay. And we can find out a relationship between our b and l. We can say that our tangent of theta will be equal to L upon B, or we can say that our L is equal to nothing but B tangent of theta. So we are going to substitute here. So we get that value of R, B will be our taken common, so this will be 1 plus tan square, and that is equal to secant square. So this comes as our secant of theta. And now we can easily find out the unit vector. Unit vector, that is our r unit vector, will be equal to our r vector divided by the magnitude, which will be giving us minus b, sorry, not minus b, but minus cos of theta and minus sine of theta. Okay. Now it is quite easy. Now we find out the field from the rod element, that is ds prime. Field due to rod element, which we are denoted as ds prime, and we can write this as our dE, because of the rod will be equal to over k, and this comes as lambda b secant square d theta, and this is b secant theta whole square, and this comes as our b secant theta, and then come our directional unit vector minus cos of theta and minus sine of theta. And if we simplify it, we are going to get that our electric field due to rod will be equal to k lambda upon b d of theta minus cos of theta and minus sine of theta. Okay. And we have found out the electric field due to our arc. Okay, let me write it here. And the electric field due to the arc was our k lambda b d theta, k lambda d theta, and one second, yeah, so I can just sort it out here. So this will be coming as b square, from here b common, so this will be b square, so entirely we can cancel, this will be only left with b, so this will be k lambda d theta upon b. So this is k lambda d theta upon b, and minus cos theta minus sin theta, minus cos theta and minus sin theta. So from here we can clearly see that these two are equal. So you can say that electric field due to our rod is equal to electric field due to our arc. Okay. And this we have taken only one single point, okay, symmetric point. And suppose if we take a point somewhere here, and on the opposite rod, same calculation, these two will be also equal. So it means for any point on this semicircle arc, there will be a same, you can say, opposite point, symmetric point rather, okay, that will be generating the same amount of electric field. Okay. And we have to remember this is, both are positive, so the direction of electric field will be opposite to each other, magnitude are same. Okay. Therefore we can say that each arc element has two matching rod elements, left as well as right. Okay. Therefore the electric field at point C will be equal to 0. That was our part A. And for part B, and part B is just a analogy between the two surfaces, so we can solve it by using the analogy. And in this analogy we have to remember, now we have dealing with part B is a 3D surface, okay, and because it is a two-dimensional cylinder and a hemispherical cap. Initially they were only a semicircular filament, like a thin wire. Okay. Therefore we can just draw an analogy between the two and solve it. Okay. So we know that our lambda will be replaced by now sigma, and rod will be replaced by the cylinder, and the semicircle will be replaced by hemisphere. So this is the analogy between the two, and C is the center of the hemisphere. Okay, so we have to remember this point C is our center of the hemisphere, center of the hemisphere. Therefore once again we can write that the surface element, you can say for surface element that is our small electric field E will be equal to K and the density small area dA, and rest of the things will be our same R unit vector, and we can divide it to same hemispherical element and the cylindrical element, like in first case we did for the element on the semicircle and the element on the wire. In this case we are going to take the element on the hemisphere. You can say that our hemispherical element, and that element will be over, in this case, our dA, and this dA will be equal to over b square and sine of theta d theta, and let me write it. So this is our dA will be equal to b square sine of theta d theta and d of phi. Okay, because it is nothing but there will be you can say two angles. One will be our longitudinal and other one will be our azimuthal angle. Okay. And similarly, we can do it for our cylindrical strip. Cylindrical strip, and in that case the small area dA will be equal to b times d phi, and okay, let me put it. So we get this as of dA will be equal to b d phi and b secant square theta and d theta. And once again, because they are having same r and same r unit vector, okay, therefore once again we can say that this electric field due to our hemisphere will be equal to our electric field due to our cylinder. Therefore there will be a pairwise cancellation. Yes, the important word I forgot to mention is pairwise cancellation. Okay, pairwise means that this ds prime is a pair of this ds. Okay, suppose here we have our point P and this is point P prime. These are nothing but pair. So it has a pairwise cancellation. So symmetric things results in pairwise cancellation. Therefore we can say that there will be pairwise cancellation. For all theta as well as phi. Therefore we get that the electric field at point C will be equal to 0. So this is true for part A as well as part B. And in case of this pairwise cancellation, if you have certain doubts or something like that, this is quite easy. Okay, so this is a semicircle and this is a point P, and so the electric field, let us suppose, in this direction, and there will be opposite pair. This is our P and this is our P prime. So because of this electric field in this direction, so we can divide this electric field into two components, okay, this as well as this, okay, and this as well as this. So this is a pairwise cancellation. So electric field will be only in one direction. Okay, but in this particular case we are having a horizontal wire also. Okay, so that will be also generating its own electric field, and that will be the pairwise cancellation resulting in upward electric field that will be further balanced by this. Okay, so our pairwise cancellation, it is much more easier to understand with respect to a semicircular wire. Okay, usually we have done this many times, and this is pairwise cancellation indirectly we also deal when we are doing the balance of the forces. Okay, suppose mostly in case of this, what we can show, the normal as well as the, suppose there is a body which is lying on a plane and there will be a mg, and we can divide mg into two components. There will be normal and this is a pairwise. Okay, so indirectly we are already doing it, but this we have to remember, in particularly in electrostatics this term is quite used that is pairwise cancellation. Pairwise means horizontal component will be balanced by the horizontal. In some case it might be result in a tangential component also. Okay, like we studied in the last video also, we found out that there is a cancellation of the tangential forces. Only the radial component is left. Okay. So this completes all the 3 questions for today. Thank you.